Hello, I just wanted to show you some of the things you can solve using Newton's second law. We have a situation here where during a head-on collision, a person in the front seat of a car accelerates from 13.3 meters per second to rest. Okay, so let's see, that means that they're actually slowing down, all right? So their velocity time graph is going to look like this. Okay, units are meters per second, seconds. This is 13.3. Okay, and it takes 0.1 seconds. Okay, so let's figure out what we can figure out here. Well, we should probably try to draw an acceleration time graph. Now, since the slope of our velocity graph is a negative slope, our acceleration would have to be down here. And this area would have to be our change in velocity, which is equal to our final velocity minus our initial velocity. And since our final velocity is 0, let's see, our initial velocity is 13.3, so negative 13.3 meter per second. And that's going to equal our acceleration A, which we do not know, times 0.1 seconds, which we do know. So that's seconds, and our acceleration is measured in meters per second squared. So from the area under our acceleration graph, 13.3 has to equal our acceleration times our 0.1 seconds. Okay, so our acceleration is going to be negative 13.3 meter per second per 0.1 seconds. Okay, so let's see what that acceleration is. I'll just go down to the calculator, bottom of the screen, and let's figure this out. 13.3 divided by 0.1 gives me 133. Oh, that makes sense. Okay. So negative 133 meters per second in 1 second, meaning that each second that passes, this car would be slowing down at a rate of 133 meters per second. Now, it's extremely large. Okay, let's see what else we can figure out here. Well, we've got an acceleration. We can figure out the displacement during this time, I believe. That would just be the area of this graph. See if we can figure that out. So our displacement while we're slowing down is going to be 1/2 13.3 meters per second times our time, which we know is 0.1 seconds. Okay, let's see what we get there. So 13.3 times 0.1, and it's going to be 1.33, I think. Yeah. Okay. So that's going to be our change in position is 1.33 meters. Okay. So what else could we figure out here? Let's say let's say we have a 10-kilogram child. No, mine are more like 40 kilograms. But anyway, let's say you have a 10-kilogram child because it's easier to calculate. How much force would need to be applied? How much net force would need to be applied on the child to actually keep them from flying out the window horizontally? That would be the Britney Spears problem. So that would be something we could use second law to find. So force diagram for the child sitting in a seat with no seatbelt, okay? And we'll just, to make things simple, here's our seat, and I'm going to draw my child, sitting straight up like this, okay? And we'll just have force due to the seat pushing up, force due to the earth pulling down, and we'll say that we'll call this FS for seatbelt. How strong does our seatbelt need to be to apply enough net force? When we add these forces, we get normal, weight, and force due to seatbelt, right? So the only unbalanced force, the sum of the forces, the net force, the resultant force, when we add these forces on the child, when we add weight, normal, and what we're calling F seatbelt, when we add these forces, we get a net force that's equal to the force of the seatbelt in length, in magnitude, and it's equal to the force of the seatbelt in direction. So what you could then do is say, well, the acceleration, which we know is huge, it's 133 meters per second, times the mass of the kid in kilograms. So MA basically has to be the same exact length as our net force vector and the same exact direction. So then to calculate MA, we would say 10 kilograms times, 133 meters per second squared, right? And that's going to be 1,333 newtons, because a kilogram meter per second squared is a newton. And this is going to be how much net force is required, which just so happens to be the same length. All of these vectors here happen to be the same length. Our force due to seatbelt, our net force, and our MA vector are all the same length. So the force required by the seatbelt would be about like that. It would be about 1333 newtons. And you should probably work the same problem out again. Maybe, let's say the person, let's just see how much bigger than the weight of the child this is. Well, the weight of the child is 100 newtons. Well, you'd have to multiply by 100 by 13. So this is 13 times larger than the child's weight. So this is a trick we use to try to wrap our brain around the problem. This is actually incredible. Imagine if your child suddenly weighed 13 times more sideways. Would you be able to keep them from flying out the window? I think you see, there's no hope if you're not wearing a seatbelt. You're not going to be able to hold your child. Unlike, Britney Spears thought she might be able to hold her child. It's not going to happen. So wear your seatbelts. And Hope you enjoyed the problem. Have a good day.